breadth first search. We're ready. Okay, so that's actually, for those who don't know, that's a maze. Okay, how does the maze game work? We have a representation of an actual maze. Okay, and then what we have is we have a starting position, and we have some, here I represent the starting position as a green cell. Okay, and I have an ending position, so I represent this ending position as a red cell. Okay, I also highlighted with a circle, with an orange circle. So what does the game ask you to do? It asks you to find a shortest path in this maze from your starting position to your ending position. Okay, so so how are we gonna solve this? We're gonna imagine that we are actually, this maze is on a horizontal, on a flat surface. Okay, and we're standing at the starting position, so we cannot see the ending position because, I mean, I don't know, the maze is made out of like these high bushes. Okay, and we want to find the ending position. So, and what do we have to solve this problem is, let's say we can just hold water and pour it onto the starting position. We can just pour water onto our cell. That's what we can do. Okay, that's how I want you to imagine that you're trying to solve it. Okay, and let's say we solve it whenever the water touches the ending position. Okay, so what will the water do when you're standing here and you're pouring water onto the starting position? What will happen is that this water now is in the cell that you are on, but it's not gonna stay there for long. It's gonna spill over the cells that are the neighbors of the cell you're standing on. So it's gonna spill over to your neighbors, right? And now these are now there are, I don't know, a bunch of cells. That is the starting one and its neighbors that contain water. And now from these positions, what will happen? Okay, again, all of these cells contain water. We can also think of them as vertices. They contain water, and there are like a frontier. There's a frontier of cells that now need to push water out to their neighbors. Okay, so now this frontier is going to be pushing water out, so now we're going to increase the number of cells that have waters. Each frontier vertex is a vertex whose neighbor has not been all filled. Okay, so it's going to be pushing water out. The frontier is a vertex that just got water and needs to push it out. Okay, so on and so forth. That's what will happen. And it's the same thing that's happening on Facebook. It's the same thing that happens with Google web crawling. It's always about this idea of, we are standing in a position and we're expanding, we're exploring, we're visiting. Okay, one step at the idea. So the idea, look at the vertices that are reachable in 0 steps. So this is your starting position. Okay, look at the vertices that are reachable in 1 step. These are your friends, or these are the cells that are neighbors of you, and so on and so forth. 2 step, 3 step, 4 step. Okay, and then you're gonna get to E. Let's play this. Okay, see here, for example, the dark blue cells those are the frontier. Those are the cells that we just poured water into, and they are pushing water out to their neighbors now. Okay, we keep repeating that. Until you're gonna spill water onto the ending position. So you found the ending position. And this guarantees, actually, we're gonna see it in a bit, it guarantees that you find the shortest path from your starting position to the ending position. Okay? So the algorithm we're gonna see is gonna actually be running in time the size of your vertices, a vertex set, plus the size of the edge set. So here, I mean, you can also see it on the maze, right? We're visiting every, I mean, if you think of, okay, we're not stopping once we reach the ending position. We're actually, let's say, continuing until we fill everything in with water. That means we're visiting all of the vertices, okay, of this graph. And here all the vertices are connected to each other. There's no vertex that's not reachable from every other vertex in the graph, okay? So if you think about it, here what we're doing is we're visiting each vertex once, and then when we visit this vertex, we are visiting its edges also. So we're visiting a vertex, we're visiting its edges. We're visiting a vertex, we're visiting its edges. Okay, now we can visit an edge more than once because we are in undirected, okay? But we're not gonna do that multiple times, okay? It's just twice. Okay, so we're gonna see in a bit. So that's the first thing. One thing we need to do while implementing this breadth first search idea is to avoid duplicates. Okay, so we're gonna avoid duplicates in what way? I just told you, right? I just told you I am on a vertex, you're on Facebook, right? You're you. That's me. Here in the maze, I mean, it's not very clear, but if you look at the Facebook example, you're you, okay, and you now go and visit your Facebook goes and visits your friends, okay. And now what does it do? Is it's gonna visit the friends of your friends, right? So what happens when it wants to visit the friends of your friends? It can also visit a friend a friend of your friend that is also your friend at the same time, right? So that means I'm not gonna just I'm not gonna just assume that this is a new person. Okay, let's say you're Alice, okay, and it visited Bob and Eve, and these Bob and Eve are friends also with each other. So in the next step, when you want to visit the friends of Bob, Eve is gonna show up in the friends, but we're not gonna include it as a new vertex that we now need to look at its neighbors, and now Bob will show up, and now Eve will show up, and so on and so forth, and that takes infinite time. You're looping at this point, okay? So that's what we're gonna be careful for, okay? So now we're ready to look at the pseudocode of the breadth first search algorithm. Okay, what does it do? It takes as input a starting position, S, a starting vertex, and then it takes also, let's assume this is neighbors is just, I assume this is just an array of pointers, or an array of, when you call it, let's say neighbors of U, it's gonna just return a list that contains all the neighbors of the vertex U. Okay, that's what it is. Okay, now you can implement it in different ways. Okay, so that's what the input is. What does it do? Now let's just recollect how we did it for the maze. Okay, so we're standing at the starting position. Okay, we already visited this position, so visited at time 0 we visited this position, so we're gonna say visited at and then set the value of S to 0. Okay, and the parent of this node is a nothing. I just started at this node, there is no parent. That's the starting position. So we're gonna initialize both visited at and parent of visited at of S to 0, parent of S to none. Okay, and these are dictionaries. Okay, so this is something that you've visited, and I've highlighted it in light blue to just show that we just visited this vertex. The water has spilled over this vertex, okay, and not just, okay, and I set an index I to 1. Now, you will see in a bit why, and the frontier is also S. Okay, I visited this vertex, and now this vertex is ready to spill water to the next, the neighbors of it, or the neighbor cells of it, okay? So that's the frontier, and that's the visited at. Okay, so here the frontier is the vertices of level I minus 1. Again, I now is 1, so I minus 1 is 0. So these are the vertices that I visited at step 0. Okay, that's what the frontier, that's what the frontier is for now in the initialization. Okay, it's all the vertices I visited first, the starting position. Now, while the frontier is not empty, and now our frontier contains the starting position, it's not empty, I'm going to initialize next. Next is going to be what? It's going to be the neighbors. The neighbors of the frontier is going to be next, okay? Next are the vertices of level I. So those I visit not at step 0, now at step 1, okay? Next, for every vertex in the frontier, I'm going to just go over each and every vertex in the frontier. What are the vertices? S. Okay, and for every vertex in the neighborhood of this vertex S, I am S. What are the vertices that are neighbors of S in the image? They are A and X, right? For every one of them, I'm gonna say, are you visited? Are you visited? Because we said we want to avoid duplicates. Did I visit you before? Are you actually a friend of mine? Or are you a new person? If it is not visited, what I'm going to do is I'm going to visit it now. So I'm going to tell you, okay, now you're visited at step 1. Okay, so I'm going to add now visited at V of visited at of A is going to be 1. And same thing, visited at of X is also going to be 1. And I'm going to also place the parent of this vertex as, the parent of this vertex as the vertex I just came from. So this is the parent. The parent of A is S. The parent of X is also S. Okay? And this is just, we're going to use it for the shortest path algorithm. Okay? So the parent is S. And now what happened? Oh, now the visited at increased. So these are visited already. Now I have water in not only in S, but in S and A and X. Okay? So that's the next also. No, sorry, that's not the next. I add to the next A and X, right? These are the next. Now these are my frontier. Okay? I added A and X. And now when I finish this, I set frontier to the next. So now the frontier is A and X. And I add to I1. Okay? So once I looped over for every vertex in the frontier, and for every vertex in the frontier and every vertex in the neighborhood of these vertices, I now visit them and now I update my frontier. And I update the I because I want to say visited at 2, visited at 3, okay? I want to calculate how many steps do I need to get to this ending position, okay? So again, for the next part, I'm gonna go from what is my frontier empty? No, we have A and X. So we reinitialize next to empty. We say for every vertex in the frontier, you have A, okay? For every vertex in the neighborhood of A, what is the neighborhood of A? Is Z. Oh, sorry, I'm going to start with X. For every vertex in the frontier, what do I have? The vertex X. For every vertex that is neighbor of X, who do I have as a neighbor? D. Okay, is it visited? No, it's not. I'm going to be visited at 2. Parent of D is X. I'm going to also append it to the next. To the list of the next, because this is going to be my new frontier, okay? Again, what do I do the same for C? Because it's a neighbor of X. I'm not done with the neighbors of X. So, is it visited? No, I put visited at 2. The parent of C is X. I put it in the next, because it's part of the next. It's part of my frontier now. Okay, and then I go, I finished with the neighbors of X. Now I'm ready for the neighbors of A. What are the neighbors of A? It's Z. Is it visited? No. So I put visited at 2. What's the parent? A. Okay. now I'm done. Next dot append, I append it to the next because now it's gonna be my frontier. Those are the vertices that just got water, wants to push it out, and they want to push it out. Okay, now I'm done. Frontier is, I've looped over all the vertices in the frontier. Now I put frontier equal next, and notice that visited has increased throughout this loop. Visited has increased, so this is all containing water. And next contains D, C, and Z, which are the vertices that I've just pushed water on, and these are my frontier now. These are the vertices that are dark blue in the maze. Okay, and I keep going. I do the same for, now every vertex. So Z, D, and C. I do the same. So I do it for C. What are the neighbors? Oh, we have a vertex. It's F. Was it visited? No. Then visited at 3. What's the parent? The parent is C. And so on and so forth. Okay? I keep on increasing the size of my dictionary and filling water. I keep on changing my frontier, okay, and visiting the unvisited vertices. And now I filled everything with water. I need to update the frontier. This is the last vertex. Now it looks around. It says, oh, are there any neighbors? Are they visited? No. So it's not going to be appending any value to the next. And because it's not going to be appending any value to the next, you won't have any frontier. The frontier is going to be empty, and you just exit the loop. You've visited every vertex in your graph, and now you have this dictionary that tells you when did you visit this vertex and what is the parent of this vertex. And what's nice about this dictionary is we're going to be using it to compute a shortest path. Okay, so I said we get as a bonus the shortest path algorithm, because using this technique we're gonna get a shortest path from each vertex, from the vertex S to each other vertex in the graph. Okay, it's not unique, but it's one of them. Okay, so for example here, if we take the vertex F, so if we go, so it's visited at 3. What's the parent of F? It was visited because of C. So C pushed water onto F. Okay, now C, what's the parent of C? C was visited because of vertex X. So we're gonna, so X pushed water onto C. And then X was visited because of its parent. What's the parent of X in the dictionary? It's S. Okay, so we're gonna, so this is a path, and you can also, see that it's it's one shortest path from S to F. Okay, and actually, you can also, you can also see the size of this path. The number of edges in the path is actually 3. So you can look up the length of a shortest path using the visited at. So you can say visited at, and you want to query for this, for the vertex F, and it will return 3, which is actually the length of the shortest path because it was visited at step 3. So it doesn't just give you, it gives you the length of the shortest path, and it gives you a shortest path between your source vertex and every other vertex in the graph. Okay, and that's how we solve this. Now we solved this puzzle. In your lab, you're gonna solve another form of puzzle. I'm not gonna tell you which one it is, but it's gonna be very much fun. Yeah, and this algorithm is very important. It's really used in a lot of much more complicated algorithms or much more complicated software. Okay.